Hello everyone. In previous lecture we see that the AC circuit. Then next point is the admittance and susceptance of the AC circuit. What is meant by admittance? Admittance is the reciprocal of impedance of an AC circuit is called the admittance. It is denoted by Y. Y is equal to 1 by Z. Impedance is also denoted by Z, which is reciprocal is also called the admittance. Then unit of impedance is ohm. Therefore, the unit of admittance is taken as a ohm. So, this quantity is useful in writing the equation of circuit in a simple manner. For the combination of impedances Z1 and Z2, Zn in the parallel, the resultant is 1 by Zp is equal to 1 divided by Z1 plus Z2 plus 1 by Zn. It can be conveniently written as a Yp is equal to Y1 plus Y2 plus Yn. Then next is susceptances. The reciprocal of reactance is also called as the susceptance. It is denoted by S. In previous lecture we see the susceptances, reactances. Then what is meant by susceptances? Susceptance is also a reciprocal of the reactances. Then it is denoted by Xc. Then susceptance is equal to 1 divided by Xc is equal to omega c is the capacitive susceptances. Then next point is resonance in LCR series circuit. In LCR circuit we have the E is equal to E0 epsilon I omega t. If this applied EMF, the instantaneous current in the circuit is. In previous lecture we see that the resonance in LCR, we see that the LCR circuit, which is last formula E is equal to E0 epsilon j omega t. Then I is equal to I0 epsilon j omega t plus or minus theta, which is plus or minus theta. Then we put in a complex form. I0 is equal to cos omega plus or minus theta plus minus theta. They where tan theta is equal to omega L minus 1 by omega c divided by R is equal to XL minus XC divided by R. Then I is equal to E0 divided by Z is equal to E0 divided by R square plus XL minus XC square is equal to E0 divided by R square plus omega L minus 2 omega c square. Therefore, when XL is equal to XC, we put a XL is equal to XC, then tan theta is equal to 0 is equal to 0. We get Z is equal to under root R square plus omega L minus omega c square. Under root R square is equal to R. That is, circuit becomes purely resistive. I0 is equal to E0 divided by Z. E0 divided by R is equal to I0 max. Then Z is equal to R, Z minimum. The current in the circuit becomes maximum. This is known as a resonance. In this case, the PD, potential difference across the inductance and conductors, become equal and opposite. Hence conductance of the each other opposite, and the resultant is only potential difference across the resistor, which is series resonance circuit, which is figure as shown in this book. First figure is E is equal to E0 sin omega t. It is a common LCR circuit. Then the resonance curve, which is I0 and I max, which is given in this circuit, and then at the resonance omega is equal to omega 0. The condition of the resonance is the L omega 0 is equal to 1 by omega c omega 0. Therefore, omega 0 square is equal to 1 by LC, or omega 0 is equal to 1 by under root LC, but omega is equal to 2 pi f. Therefore resonances F is equal to f0 resonance frequency. It is given by f0 omega 0 divided by 2 pi 1 by under 2 pi under root L into C. At the resonances omega is equal to omega 0, then the condition of the resonance is L omega 0 is equal to 1 by C omega 0. Therefore omega 0 square is equal to omega 0 is equal to 1 by under root L C. Then therefore resonance F is equal to f0. Resonance frequency is given by f0 is equal to omega divided by 2 pi is equal to 1 divided by 2 pi under root L C. Then next point is a voltage amplification in series resonance circuit. At the resonance, potential difference across the inductance and condenser are equal and opposite. They cancel each other. Therefore circuit becomes purely resistive, and the function of the applied EMF is to only overcome the opposition due to resistance. Voltage amplification in the series resonance circuit. At the potential difference, if the inductance and conductance are equal and then opposite to each other, then it is which is cancel each other. Therefore the circuit is also a pure resistive, and the function of the applied EMF is a only opposition due to the resistance. This is known as a voltage amplification. Sometimes it's called as a magnification. This circuit is also connected in the series in the circuit is a large reactances. Potential difference across it increases to the very high value. Voltage amplification is equal to potential difference across the inductances or capacitance divided by applied EMF. Then omega Li0 divided by Ri0 is equal to omega Li0 divided by under root 2 Ri omega 0 I'm RMS in omega 0 L divided by R is equal to, since omega is equal to omega 0, since L is a large, omega L is very greater than equal to R, hence the voltage amplification is very high. For high frequency, omega L divided by R can be designated to magnify the voltage to the desired value. If the frequency of the applied EMF is varied, then the series LCR circuit supply will give a maximum responses, that is pass maximum current will have a maximum potential difference across the inductances at a particular frequency called the resonant frequency f0. Hence the voltage magnification is a very high as the resonant frequency. This procedure is used to tune a radio or the television receiving set to the desired station. This procedure is also used to tune a radio or the television receiving set to the desired station, sending a signal at a particular frequency. This circuit is also known as a acceptor circuit. Then next point is a quality factor. Quality factor, which is also depend on the bandwidth of this in this experiment, is also. So the quality factor is also called a quality ratio. It is also defined as a Q is equal to 2 pi into maximum energy stored divided by energy dissipated per cycle. Q is equal to 2 pi into maximum energy stored divided by energy dissipated per cycle is equal to 2 pi divided by T into maximum energy stored divided by energy dissipated per cycle divided by T. Then omega into maximum energy stored divided by average power dissipated. Therefore in the AC LCR circuit containing the inductances L and series resistances R, then QL is equal to omega into half Li0 square divided by half into Ri0 square is equal to omega L divided by R. This is the equation of the inductances. As seen in this part A, the article omega L divided by R, and hence QL is also represent the voltage amplification. Similarly, the quality factor AC of the circuit containing the condenser C and resistor R in the series QC is equal to 1 divided by omega CR. The value of the QL and QC are same as the value of the sec theta of the quality inductor and capacitor respectively. Hence Q is the quality factor of the reciprocal of the power factor cos theta. Sharpness of the resonances in the series circuit. In an LCR circuit current increases as the angular frequency omega of the applied EMF increases. At a particular value omega 0 it becomes a greatest. This is called the resonances. At this value omega 0 L is equal to 1 by omega 0 C, that is F is equal to 1 by 2 pi under root LC. If the width of the curve about the resonance frequency omega 0 is a small, the curve and the resonance set are said to be sharp for a given value of the L and C. Variation of the sharpness with the resistances are as shown in this figure. As the resistance decreases, the sharpness is also increases. Sharpness of resistances means the value of the current is also increases or decreases, which is depend on the resonance curve. That is, this value is called in LCR circuit. The angular frequency omega of the applied EMF is also increases or the decreases. This is called the resonance. So F0 is equal to 1 divided by 2 pi under root LC. If the width of the curve about the resonance frequency omega 0 is small and the curve and the resonance are set to be sharp,